Hello, in this video we're going to look at the idea of exponential equations and exponential growth. This is an idea you may not have seen before, and you wouldn't have seen it in previous math courses here at Yavapai College that you have taken up to this class. But we're going to look at exponential equations, how they're used, what their graphs look like, how to solve them, and in order to solve them we're going to bring in the idea of logarithmic equations. The one piece of this lecture the one thing that this lecture is not going to cover is the idea of logistic growth. In the book, I believe that's pages 330 through 333. So we don't need to worry about that idea. So let's go ahead and get started with exponential equations. So here is the notes, and what I want to do is I want to start off by just doing a little experiment. And you can do this along with me as I'm working through it. I want you to fold a piece of paper in half and continue to fold it over and over and over again and record the number of spaces that are created in the piece of paper. Continue to fold the paper and record the number of spaces 4 times, and then we're going to see if we can figure out what might be happening on the 5th time. Alrighty? So, take a piece of paper, and I have a piece of paper here, and fold that paper in half. So I took that paper and I folded it in half. It might be easier to see it on the video screen, so let's do that. Okay, so I've got a piece of paper here, and I'm going to fold it in half. And when I do that, the number of spaces that I've created are 1, 2. All right. Now I'm going to fold that paper again. And now the number of spaces that have been created, 1, 2, 3, and 4. All right, and when I fold it again, and I count that, now I've got 1, 2, 3, 4, 5, 6, 7, 8. All right, so you can go ahead and fold your paper. Our results. So when I had no folds on my paper, there was only 1 space, the whole paper. Okay, and I'm going to leave myself a little room here because I'm going to try and write what's happening. When I had 1 fold, remember that was 2 spaces. Okay, when I had 1 fold, I had just the 2 spaces, the one on the left and the one on the right. When I had 2 folds, 1, 2, okay, that's when I was up to 4 spaces. And when I did 3 folds, I had 8 spaces. When I do 4 folds, which is getting pretty small, okay, for me it's looking about like that. And when I fold it back out, and you count those spaces, you have 4 rows of 4, which is 16. Now, when I look at that, what I see is I notice that these are all powers of 2. And even this one that is 2 to the 0 power, because we remember that anything to the 0 power is always 1. And 2 to the first power would be equal to itself. 2 squared, we remember, is 4. 2 cubed is 8. 2 to the 4th is 16. So what we think should happen for 5 folds would be 2 to the 5th, which would be 32. And if you take your paper, all right, and make a 5th fold, okay, and then count those, you should get 32. Just a little bit of trivia. I think the most number of times that you can fold a piece of paper, no matter how big it is to start with or how small, I think the maximum number of times you can fold it is 7. It's either 7 or 8. So you can kind of try that just for fun on your own. All right, so notice what that gives us is it gives us an idea as to how we could model this situation. We could take the spaces, let's let S be spaces, and we could say that's equal to 2 to the n for number of folds that we have done to the paper. So if we have no folds, 0 folds, we would get 1 space. one fold, we would get 2 spaces. 2 folds, we would get 4, etc., etc. Notice what we have here is we have something a little different than you've probably seen before, and that is we have a variable, and it's in the exponent. In the past, we've always had numbers up in our exponents. So what I want to do is I want to look at how to graph a basic exponential equation. Alrighty, so what I have here is y equals a times b to the x. And notice we could even write this in that form, and we'll do that in just a little bit. But if I want to graph that, what I'm going to do is I'm going to, and for some reason, my printer printed that very, very lightly. I'm not quite sure why. What I'm going to do is I'm going to graph that. Hopefully yours printed a little better than mine. And here is my y-axis, and here's my x-axis. And I'm going to come up with some points, x and y. And I'm going to use -3, -2, -1, 0, 1, 2, and 3. Okay? So let's start down here and work our way back up. When I put a 3, and let's just do y equals 1 times 2 to the x, which is the same as what I have here. So if I'm going to graph this, I plug in a 3 for my x. 2 to the third power is 8. 8 times 1 is 8. So that gives me the point 3, 8. 1, 2, 3. 1, 2, 3, 4, 5, 7, 8. Up here. Okay? Then I'm going to plug in a 2. 2 squared is 4 times 1 is 4. So I have the point 2, 4. I'm going to plug in a 1. 2 to the 1 is 2. 2 times 1 is 2. So I get 1, 2. 0. 2 to the 0 is 1. 1 times 1 is 1. So I get 0, 1. -1. When I plug in a -1 up here, remember what that does with a negative exponent is it uses the reciprocal. So 2 to the -1 is equal to 1 over 2 to the +1, or 1/2. So when I plug in a -1 here, I get 1/2 times 1, which is 1/2. So -1, 1/2. When I plug in a -2, I get 2 to the -2. That would be 1 over 2 to the +2, or 1/4. So I get 1/4. And then when I plug in -3, 2 to the -3 would be 1 over 2 to the +3, which would be 1/8. So here's what my graph looks like. And if I connect all this stuff, what I'm going to find is that basic shape is like that. Okay? Little different than some of the graphs you've seen before. It's not a parabola where it's going to come back up. Alrighty? It's going to head down towards the x-axis. And is it ever going to cross the x-axis? Well, if I plug in x values here, am I ever going to get a 0? The answer is no. I'm going to get smaller and smaller values. If I have 2 to the -100, that's 1 over 2 to the 100th, which isn't 0, but it's really, really small. So the x-axis acts as what we call horizontal asymptote. Okay, horizontal asymptote. So that's what we've got here. Now let's talk about what this A and what this B represent. So if we look at it in terms of what we had here, A, we have y equals A times B to the x. Well, if we were using it in terms of what we were doing here, we would say y is equal to number of spaces. We would say that x is number of folds. The A which is 1, we call that our initial amount. In other words, when you start with a piece of paper that has no folds, 0 folds, the initial amount of spaces is 1, and that's what our value for A is. And then B was what was happening every time. It was how fast the number of folds was growing. So we call that our growth rate. All right? And that's the basic idea behind exponential equations. We're going to have our variable in the exponent. So let's continue on with this same problem, but ask another question from it. So if it were possible to fold a piece of paper 25 times, and remember I said the most you can fold it, I believe, is either 7 or 8, how tall do you think that paper would be? And it says a ream of paper contains 500 sheets and is approximately 2.5 inches tall. So what I'm going to do is I'm going to use my equation, y equals 1 times 2 to the x, and I'm going to say I want to find out what happens with 25 folds. So y equals 1 times 2 to the 25th. All right, in order to do that, I'm going to use my calculator. And the button I'm going to use is this button for exponent. And I'm going to put in 2 raised to the 25th power. And notice I get a very large number. So I get 335544 So 35,554,432 spaces is what's going to happen. Alrighty. Now, so if we think that each of these spaces is basically the thickness of a piece of paper, then I want to find out how many reams of paper that would be. So each ream contains 500 sheets. So if I divide this by 500, I should get how many reams tall that is. So I'm going to take this and divide it by 500. So 33554432 divided by 500 gives me 67,109 approximately. So it is 67,000 reams of paper high. Each ream is 2.5 inches tall. So let's next go ahead and figure out how tall that is. So I'm going to multiply that by 2.5 inches each. So 67,108 times 2.5. And I'm just leaving the numbers in there so that I don't have to redo this every time. I get 167,772 inches. Well, most people can't picture 167,772 inches. So what I'm going to do is I'm going to use something that we'll get to a little later in the course, which is unit conversion. And I'm going to convert that into miles because I think that might be easier to look at. So I'm going to take, rearrange my paper here. I'm going to take 167,772 inches, and I'm going to put it over 1, make a fraction out of it. I'm going to multiply it by, I'm going to get rid of inches, so if I put inches in the denominator, it'll cancel with this inches, and I'm going to change it into feet. And I know that there are 12 inches in 1 foot. So this is what we call a unit fraction, and we'll get into that later on in the course. So the inches will cancel, and what I can do is I can divide by 12 to figure out how many feet there are. But I'm going to keep going and do one more calculation. Now I want to get rid of feet, so again I'm going to put it down in the denominator so it'll cancel. And I'm going to change that to miles, and I know there's 5,280 feet in 1 mile. So what I'm going to end up doing is I'm going to end up taking 167,772. I'm going to divide it by 12, and then divide it by 5,280. And what I'm going to get is I'm going to get about 2.65 miles. All right, so if I was able to take a piece of paper, fold it 25 times, the number of sheets that would end up, or spaces that would end up being created, would end up being 2.65 miles high. Notice that's why the maximum that you can do, and I'm pretty sure it's 7. The max is 7 times. Otherwise, it just starts getting too thick, and you can't mess with it anymore. All right, let's go on to another place where exponential growth is used a lot, and that's in the idea of population growth. So it says the 2000 census, and I'm just going to go ahead and read through. You've got those notes that you can look at. The 2000 census counted roughly 281 million people in the United States at a time when the yearly population growth was about 1.2% per year. If this growth rate continues until 2044, what will the population of the United States be at that point? So 1.2%, we need to change that into a decimal. So remember, we do that by moving the decimal point 2 places to the left. We'll do a little bit more with percents in the next section, in the next chapter. So we get 0.012 is our decimal equivalent of 1.2%. So let's see if we can come up with an equation for this. We have y equals a times b to the x. We need to figure out what all these things mean. So x, let's let that be the number of years, because that's one of the things that's changing, is the number of years. Number of years, and let's make it since 2000 so we have easy numbers to work with. All right? So what we've got is we've got number of years is changing, and what's changing over the time? The population. So let's let y be the population. And again, in order to make it easy, let's make it in millions. All right, now we need the a and the b. So we set up above that a is our initial amount, and it's our initial amount of population, since that's our y variable. So our initial amount of population back in the 2000 was 281. And I'm just going to write that as 281 since we're doing our population in millions. And now for our b, we need our growth rate. Now you would probably think that it would just be this percentage up here. Okay? But that's not quite right, because what's going to happen is we're going to say we're going to start with 281, and we're going to add 1.2% of 281. So really what we get if we factor the 281 out is we get 281 here plus another 1.2% of 181. So we actually get 1.012, and this is our growth rate. So this is not correct, and I want to use 1.012 instead. So now I'm ready to write my equation. So I get y is equal to my initial, which is 281, times my growth rate, which is 1.012 raised to my x. Now, remember, I wanted to know if this growth rate continues until 2045, what will the population be? So I want to know what my y is, and I know that my x is going to be, well, I'm not going to use 2045 because remember we said it was the number of years since 2000. So x would be 45. So I'm going to plug that in. Y equals 281 times 1.012 raised to the 45. I'm going to do that on my calculator. So I've got 281 times 1.012 raised to the 45. And that gives me, I'm going to round that off, about 480. or 481 if I round it off correctly. So y is about 481. So what that means, remember, y is the population in millions. So about 481 million people would be our answer. All right, let's move on to the next page. And we'll look at another type of use for exponential equations, and that is the idea of compound interest. So let's suppose that you deposit $1,000 in an account that pays 8% interest per year. How much interest would be in the account after 5 years? So at the end of 1 year, what's going to happen is you're going to start off with what you deposited. So you deposited $1,000. Plus, you're going to add your interest onto that, and your interest was 8%, or 0.08, of the $1,000. What I'm going to do is I'm going to rewrite that, and I'm going to pull out the 1,000, and I'm going to have a 1 left over from here, because this is times 1. If I factor out 1,000, I'm left with 1 plus 0.08, which would be 1.08. Alrighty. At the end of the second year, what's going to happen is I'm going to take what I had at the end of the first year, which was 1,000 times 1.08, and I'm going to add 0.08 times that amount. Okay, so now I'm earning interest on my interest, which is why we call it compound interest. Notice again I've got this in common, so I'm going to factor that out, and that's going to give me 1,000 times 1.8 times, if I factor those out I get 1, because this is times 1, 1 plus 0.08 again, so I get 1,000 times 1.08 squared. Okay. Now let's go down to the third one. For the third one, I'm going to take what I had from the last one, which is 1,000 times 1.08 squared, plus 8% times 1,000 times 1.08 squared. And that's going to give me, well, I've got this in common, so I'm going to factor it out. 1.08 squared. And what I'm left with is one of those plus another 0.08 of those, so 1.08. Notice these can be combined, and I will get 1,000 times 1.08 cubed. Now, are we seeing a pattern here? You bet we are. Notice I've got my initial amount times 1.08 times 1.08 squared times 1.08 cubed. All right. So for the next one, I could just go straight to it and say it's 1,000 times 1.08, and since I've got 4 years now, that's going to be to the fourth, and this is going to be 1,000 times 1.08 to the fifth. So if we were to take and make an equation out of that, all right, again using our y equals a times b to the x, and see if we can figure out what these are. Let's replace the y with an a for the amount of money, and let's replace the x with a t for the amount of time. And let's just write down what all these things mean. So a is the amount of money, b is the number of years. What would a be? Well, a would be our initial amount. So a would be $1,000. B is our growth rate. So what are we growing by each time? the 8% added to what was originally there, so our growth rate is 1.08. So that gives us our equation of A equals 1,000 times 1.08 to the t. There's our equation. Now what we want to do is we want to figure out how to solve that for something. Let's say I want to know how long it's going to take to double what's in there. All right, so here's my question. I'm going to use my equation A equals 1,000 times 1.08 to the t. And if I want to know how long it's going to take the amount in the account to double, my A is going to be 2,000. And now I need to solve that for t. So let's just go ahead and do what would naturally be in our inclination to do. First thing would be to divide both sides by 1,000. And that gives us 2 equals 1.08 to the t. Now, we're not sure how to solve this. So what I'm going to do is I'm going to throw something in here, and we're going to see if it works, and then we're going to talk through what I'm actually doing. What I'm going to do is I'm going to use something called a logarithm. And I'm going to use a certain property of a logarithm, which I have written down here. So I'm going to take the logarithm of both sides, and I'm going to write that as log. So I'm going to take the logarithm of the left side, and I'm going to take the logarithm of the right side. And what the logarithm is actually going to do is it's going to do the inverse operation of this exponential. When we had something like x squared equals something, and you wanted to solve that, you did the inverse of the squaring, which was the square root. If you had 3 times x and you wanted to solve that, you did the inverse of multiplication, which was a division. So here we've got an exponential, and the inverse of that is going to turn out to be logarithm, and I'll show you a little bit more about that in just a second. So I'm going to take the logarithm of both sides, and what I'm going to do is I'm going to use this property down here which says if you have a logarithm of something and it's got a variable in it as the exponent, you can actually pull that variable out in front and make it a product. So I'm going to take this t and pull it out in front and make it a product. And now this is actually just a number, so this is some number times t, and so in order to undo the multiplication here, I'm going to divide both sides by logarithm of 1.08. Okay, so if we go to your calculator and look at your calculator, on your calculator you have a button that says log, and that's what I'm going to use here. So I'm going to type in log of 2, and notice it gave me an automatic parenthesis, so I'm going to close that parenthesis, divided by the log of 1.08. And what I get is about 9. So I get that t is about 9, so about 9 years. Now, is that accurate? Well, let's go back in and plug 9 years into our equation. So here's our equation right here. Let's plug 9 into that equation. So if I have 1,000 times 1.08 raised to the 9, what do I get? Pretty darn close to 2,000. Okay, and if it wasn't some rounding error, it would be 2,000. So that seems to work, but if we look at the calculator, there's a log, and there's also something called ln, which is another type of log. And what's interesting is I can either use log, L-O-G, or I can use ln, and they both work the same. So if I was to do this again with ln instead, so ln, oops, turn it on, ln of 2 divided by ln of 1.08. We should get 9 again. In fact, notice these answers are identical. Okay, so it doesn't matter which of those buttons you use, they're both going to work the same way. So, here's just a quick definition of what a logarithm is. A logarithm is basically another way to take an exponential statement and rewrite it. So it says 2 cubed, or 2 to the third power, is equal to 8. Well, that's the same as writing log to the base of 2 of 8 is equal to 3. So notice what it's doing is it's saying, if we take this as our base, and we take this as what we're trying to get, the logarithm will get us what the exponent is. But the important property that we're going to use is that if we take the log of something that has an exponent in it, we can pull that exponent out in front and make it a multiplication. So how would we solve these types of logarithms here? Well, if we have 2 to the x equals 15, I would take the log of both sides. For this one I'm going to use log, for the next one I'm going to use ln. And what that means is we just have logs with different bases. Okay, log is equal to log base 10, and ln is log with the number e as the base. All right, so log of 2 to the x equals log of 15. And I'm going to use this property that says I can take this exponent and bring it out front as a multiplication. So x times log of 2 equals log of 15. And then I'm going to divide both sides by log of 2. And then I'm going to use my calculator. Log of 15 divided by log of 2. And I get about 3.91. And you can always check these by plugging that value back in. So if you were to say, let's find 2 raised to the 3.91 power, okay, notice what you get? You get about 15, which is what we have here. So let's try one more. So if I have 5 to the x equals 35, I'm going to take the log, this time I'm going to take natural log, the ln, of both sides. Alrighty. The property says if I've got an exponent, I can pull it out in front as a multiplication. And then just divide both sides by ln of 5. And when I do that, ln of 35 divided by ln of 5 gives me about 2.21. And again, if you would check that, 5 raised to the 2.21, it comes out to about 35. All right. So that is the idea of exponentials and logarithms. Now, if you've got something that's not quite as straightforward as one of these, if you've got something more like this problem up here, the first thing you're always going to want to do is you're going to want to isolate that exponential. Because once you got that exponential isolated, then it's just a matter of taking the log of both sides and solving from there. Alrighty. So if we go back up to this one last time, this equation, we can actually rewrite this a little bit more general in terms of compound interest. And the formula for compound interest is A equals P times, and A is our amount at the end. Okay. P is our, we call it the principal. It's the amount at the beginning. Then we had 1 plus our R, which was our interest rate. And remember, that has to be in decimal. And that was raised to the T, and this was the time in years. Okay? And this is a formula that you'll see in the book, and that's where it comes from, this whole idea up here. So that's your introduction to exponentials. I hope that was helpful.